Welcome to the ISTEM Strategies Project by Rebecca Yaple. I will be focusing on a collaborative learning strategy with a hands-on approach in an at-risk setting. The purpose of this PowerPoint is to introduce what the definition of ISTEM is, introduce collaborative learning as a strategy in the classroom, and teach the engineering design process. These will all be done in an at-risk setting. I have a unique opportunity as I teach for a school with at-risk children. With this experience, I plan on showing how ISTEM can be integrated into a non-typical classroom. First, we want to talk about what ISTEM is. Integrative STEM education, or also known as ISTEM, is a way for students to learn about the different disciplines in STEM. According to Sanders and Wells in 2010, ISTEM is a technological and engineering design-based learning that intentionally integrates content and process of science and/or math with technology and/or engineering. The most important part of the definition and organization of ISTEM is the design-based learning. Each discipline works on problem-solving skills and has a specific design process to follow. Without these processes, students do not get the full ISTEM education. It is believed that teachers of STEM education have their own discipline to teach, but their joint base is ISTEM. Disciplines need to rely on technology and engineering to further enhance the integration into their subjects. My targeted audience for this project is a high school geometry classroom. In the Virginia Beach City Public School System, this is typically taken in 10th grade. I am focusing on an alternative education setting which will still put them in a 10th grade classroom, although their ability levels may be significantly lower. I want to start by giving a definition of at-risk students, and according to Ernst & Moy, they are students who are identified with at-risk indicators such as disabilities, students from economically disadvantaged families, or students with limited English proficiency. Many times, these students come with a lot of baggage that can hinder the classroom learning environment. These students have a strong effect on taking ISTEM into the classroom. Many times, these students have low self-esteem, which leads to low confidence in their abilities. Also, they have little or no knowledge of the STEM disciplines. They usually do enough to get by, but do not work towards these subjects. They can sometimes lack social competence and have horrible social adjustments. Student just wants to fit in, not to be the one to stand out and eventually get something correct. Collaborative learning is being used extensively in classrooms. It is defined as two or more people working together to learn something. One collaborative learning type that has shown consistent results in the STEM disciplines is the peer-led group. In this type of collaborative learning, students are expected to teach themselves. Peer-led team learning is a version of collaborative learning that has shown consistent success in technology, science, engineering, and math, according to Light. During these projects, as the teacher, I would not be helping the students through the process. They will be using the engineering design process, which I will talk about later, to learn what they need to know to facilitate their own learning. Hands-on learning is one of the best practices to use in the classroom. Many students find this type of learning to be most beneficial. In a study by Mativo and Park, they found that students thought hands-on learning was beneficial, interesting, and useful. These are the three of the most important words to hear as a teacher. Combining collaborative learning with a hands-on approach, students will be teaching themselves something beneficial to solving real-world problems. This becomes especially crucial in a math classroom where many students do not feel as necessary to learn, as they will never see the process of how they could use it in the real world. The engineering design process is found in an article written by Dr. Ernst for the Mississippi Valley Technology Teacher Education Conference. The first step in the diagram starts with understanding the problem. This allows students to complete research, brainstorm some possible solutions, and make sure to comprehend the requirements. Step 2 deals with developing a plan. This is when students will be making sketches and elaborating these drawings as they continue to design and brainstorm together. The third step continues with carrying out the plan, and probably the student's most favorite part. Students are to act on their drawings and create their project. Although their projects may change from what the plan and sketch originally had been defined as, at least they will have a backbone to go off of. The final step is the evaluation, which is to make sure the project fits the requirements, and if not, repeat the process again. Once it fits, they will be presenting their projects to the class. The bridges will then be tested to see how much weight they can hold, as it is used as a competition to see who can hold the most weight. Once students learn the engineering design process, they can relate it to any of their classes. These designs can be used in mathematics when faced with a difficult problem, or in science when working with an experiment. The process could directly be related to the scientific method, which every student learns about every year in their science course. This teaches students an application of the process and how it cross-correlates through other subjects. Instead of learning different ways to solve a problem, they can change a few steps and use the design in a different course. With this knowledge, engineering should not be prohibited from participating in the ISTEM education approach in all subjects. The right side of this slide lists the modifications and advantages for at-risk students. By introducing a less structured project-based learning objectives, students can alter their mindset. It allows for creativity and multiple solutions. Many times, you will get a project and you will give a less structured project and you will get 10 different solutions from 10 different students. Also, many times being in an at-risk program, students need specific differentiation to fit their individual IEPs. Giving a collaborative learning, less structured product allows all students to succeed, as they will not know what each person has on their sheet. Some may be given more information that will guide them through the process, while others will be given significantly amount less. It all depends on their IEPs and their objectives and goals on these IEPs. The first step in the process is going to be research. Students will start by researching famous bridge and structural designs. Some students will be given specific bridges to research, while other students will be expected to do it on their own. They will be expected to answer questions to verify their research. They will be looking up shapes that hold the most structure, which is what ties into geometry. Students will be doing research independently and then combining their ideas to see if the research matches. If it does, they can move on with the project and come up with an idea. If it does not, students will have to decide together which design they would like to go with. English focuses on persuasion in high school, and this is a great way to introduce it into the mathematics classroom. The Standards for Technology Literacy Standard 1 allows for creativity and goal-oriented research. The student's goal is the types of structures that will best support the weight. Students will need to make sure they spend a good amount of time researching, as it will potentially prevent them from having to go through the design process again to build another bridge. Standard 9 deals with the understanding of the engineering design process. The engineering design process involves defining a problem, generating ideas, selecting a solution, testing the solution, making the item, evaluating it, and presenting the results, all of which the students will be completing. If students understand the process, they can follow the steps to make sure they build a bridge that fits all the proper requirements. Planning is an important part of this learning strategy. Students need to plan their design instead of jumping to start it. With a proper plan, they can use their research from step 1 to determine what the bridge can look like. Also, the planning will help to enhance their knowledge of different topics of geometry. They can map out their minimum and maximum dimensions to make sure it fits requirements. They will also be expected to determine what types of shapes they are using and why it is a better choice, which will focus on Standard 9 for geometry, that states the students will verify characteristics of quadrilaterals and use properties of quadrilaterals to solve real-world problems. The students may or may not use quadrilaterals in their problem. However, there will be some type of quadrilateral they will have to be defining. Another standard to cover would be Standard 13, which wants students to use formulas for surface area and volume of three-dimensional objects to solve real-world problems. Students will be expected to find the surface area of their bridge to determine the cost for materials needed. Step 3 is the students will be most looking forward to. They will start using their resources available in the classroom to design their bridge. This focuses on Standard 11 from the Standards for Technology Literacy that focuses on applying the engineering process. Students will be expected to take their sketch and make it into a reality. This is a hands-on approach, no longer just on paper. This step will keep the students most interested, as they are no longer looking at research on a computer or just drawing a picture. They are finally allowed out of their seats to do work with their hands. The final step is the evaluation stage. When dealing with the evaluation stage of the engineering design process, the students will be using self-evaluation with formal assessments. The questions that will be evaluated are, does it meet the dimension requirements? How much weight can it hold before it breaks? Did they follow the engineering design process? And what could be done next time to make it better? The students will be making hypotheses about how much weight their bridge can hold and why they believe this. This will help the students realize if they need to go back through the process again to design a better bridge. If they do not meet the evaluation, they can repeat the process. If they meet the requirements, they can proceed with the evaluation and see how much weight their bridge can actually hold. The buy-in for this project is a few simple reasons. This strategy of combining hands-on learning with collaborative learning to build bridges gives students a new approach to learning. This approach helps to keep students interested. They get to see how much math they are learning about in class relates to the real world. In an at-risk setting, most students are highly unmotivated. This project gives students a stronger motivation as they are no longer taking notes or reading a book, but applying what they learn to the real world. This project also helps students build their team and social skills. They do not always have time to interact with their peers in class, so this allows for interactions that can be persuasive but also productive. I hope you have enjoyed my presentation on collaborative learning and building bridges in an at-risk setting.